Hi everyone, I'm Sherry. I will be talking about dichotomy of control, separating what you can control from what you cannot. This is joint work with Dale, Peter, and Ophir. So we're looking at offline sequential decision making. And a popular approach to this problem setting is known as offline RL, which given an offline data set, tries to learn an optimal policy using existing RL algorithms. But offline RL is not the only approach to extract expert policies from existing offline data. Another approach that's becoming increasingly popular is called return condition supervised learning. And such approach includes methods like decision transformers. And how this approach works is by conditioning on a future sum of return to decode the action sequence that is associated with this future sequence. And at inference time, by hoping that increasing the return that the policy is conditioned on, we might encourage the policy to decode more expert-like actions. However, this return condition supervised learning approach actually fails in stochastic environments. So to demonstrate this, let's look at an example. Let's assume that we have two trajectories in the offline data set. The first trajectory has a probability of 0.01 of receiving a huge reward of 100. And the second trajectory has a probability of 1 of receiving only reward 10. So in expectation, the second trajectory is preferred. So the action A2 is preferred because the expected value is 10, whereas taking the first action A1 will result in an expected value of 1. But when we condition on the reward 100, we will decode action A1, which is a result of the lucky transition is unlikely to happen because in practice, when we take this action, there's a much higher probability that we wouldn't get that reward. And a funny analogy here is, should we condition on the result of winning $1 million to buy lottery, or should we just do our proper investment strategies? So another way to look at the failure of return condition supervised learning in this stochastic environment is that the return condition supervised learning is not making a distinction between two sources of stochasticity. There is the stochasticity from the policy, which is under the policy's control, and there is the stochasticity from the environment, which is uncontrollable. The right thing to do here is to separate these two sources of stochasticity and only maximize over the controllable actions while taking the expectation over the uncontrollable environment transitions. So to this extent, we propose dichotomy of control. And then the name comes from the Stoic philosophy saying that please grant me the serenity to accept the things that one cannot change, the courage to change the things that one can, and the wisdom to know the difference, hence the name dichotomy of control. Okay, so with that overview out of the way, let's talk about the main presentation. So I will go through the formal problem setup, and I will talk about the dichotomy of control objective, give you some theoretical guarantees, and finally present the experimental results. So let's remind ourselves that we're talking about return condition supervised learning, which given a fixed offline data set consisting of episodes, tau, and some future aggregation functions, such as the total sum of future reward. The return condition supervised learning approach tries to learn a policy pi using maximum likelihood while conditioning on the future return. And oftentimes people are using non-Markovian policies to condition also on the episode history and using a transformer to encode that history. It's becoming an increasingly popular practice. So that's why we focus our setting on the non-Markovian setting. And the inconsistency can be defined as the actual value of a policy that achieves in an MDP which is the expected value of future reward. So this is the typical notion of a value function, is different from the quantity that the policy is conditioned on, which is z. Because in our previous example, we see that the expected value associated with taking action A1 is only 1, but the conditioning value is 100. So this is where the inconsistency arises. So one might think that conditioning on the total sum of return is the culprit here, because this reward, total sum of reward, actually depends on the entire trajectory, which contains the stochastic environment transitions that is not under the policy's control. So one attempt to mitigate this inconsistency might be to try to condition the policy on a stochastic latent variable representation of the future as opposed to a scalar reward. So we might learn a posterior distribution of z conditioned on the entire trajectory and regularize the posterior with some using KL divergence with some prior PZ that only conditions on the past. But notice that this doesn't fundamentally fix the inconsistency issue because this KL divergence is still looking at the entire trajectory and it's making no distinction between the controllable actions and the uncontrollable transitions. So instead of the VAE objective, we can propose the dichotomy of control objective. So the first part of the dichotomy of control objective actually looks very similar to the return condition to the future condition supervised learning objective, where we have a maximum likelihood objective conditioned on some latent variable representation z of the future. But notice that the constraint is different. So instead of imposing a KL constraint, we propose to impose a mutual information constraint between the stochastic future representation z and the stochastic latent variables of the environment, which are the reward and next state transitions. So this objective, this mutual information constraint is essentially saying that the latent variable representation of the future should not contain any information about the future stochasticity of the environment, which are the stochastic rewards and stochastic next state transitions. So to learn this, to impose this constraints in practice, we can transform this mutual information constraint into a contrastive learning objective where the next states and rewards associated with the Z are the positive examples and the reward and transitions randomly sampled from the offline data set are used as negative examples. So one thing that's that is kind of tricky about the dichotomy of control is that after we've learned the policy using this objective, how do we actually use this policy in practice? So we wanted to choose the Z, which is the stochastic representation of the future, that will lead to highest expected return. So to do that, one approach is we can sample a bunch of stochastic latent variables, Z's, and we can select the Z that has the highest future expected value. So in order to do that, we need two additional quantities, which is a prior to sample z's from, which is the pz conditional S0 here, and some value function to evaluate which z is good. And notice that we have a stop gradient around the posterior and the prior. This is different from the VAE objective because we don't want the prior to affect the posterior of z. So now with the learned prior and the value function, we can simply just sample a bunch of z's during practice and take the z that has the highest predicted future predicted value. And next, let me show you some consistency results to make sure that the dichotomy of control objective is actually consistent. So let's remind ourselves what the definition of consistency is. So we say that a policy pi and a value function v are consistent only if the value predicted from z is equal to the actual value that a policy achieves in an MDP. And with mild assumptions that the data and the environment have the same next state transition probabilities, and the assumption that there's no approximation or optimization errors, we can show that the dichotomy of control objective with the mutual information constraints are indeed consistent. And in our paper, we have additional results to show that this also holds for Markovian policies, which are more typical in traditional RL literature. And lastly, let me present you some experimental results. There are more experiments in the paper, but I wanted to walk you through this simple Bernoulli banded example. So in the data set, we have reward 1 with equal probability of taking the arm A1 and A2, because in the data set, the probability of reward equals to 1 equals to P times 1 minus P for both arms. So condition on reward 1, the return condition supervised learning policy is going to be indifferent between the two arms. It's going to choose the two arms with equal probability. That's why you see that the return condition supervised learning objective always only achieves 0.5 of the reward. But in practice, we want to select the arm that has the higher Bernoulli parameter, right? So we see that the dichotomy of control objective is able to choose the correct arm, whereas the other objectives fail. And furthermore, we show, because the previous example is only taking care of stochastic reward, and then to take care of the stochastic transitions, we show a stochastic grid walk example. And we again see that the dichotomy of control objective is better than the VAE objective and is better than the decision transformer objective. And behavioral cloning or percentage-based behavioral cloning fail miserably in this environment. So let's recap. The first thing we identified is a failure of the return condition supervised learning approach. We noticed that they actually fail in stochastic environments, which is often what reinforcement learning cares about. And second, we propose a dichotomy of control objective, which is based on mutual information. And we show that this objective, both theoretically and empirically, leads to consistent policies that performs well. And here are some remaining questions. As we enter the era of large models for perhaps decision-making, the one thing that we ask ourselves is, what else that is special about offline RL that return condition supervised learning cannot do? So one example is stitching, which is to compose suboptimal trajectories. That is not covered by this work, but there is signs of hope that people can work in this direction. And another future open question is the application of dichotomy of control to real-world stochastic environments. And one such environment is dialogue, because the humans that a dialogue interacts with is a stochastic entity, because what we say is indeed stochastic. And a good dialogue agent might try to maximize the expected return as opposed to some one-off return of a particular human. So, and lastly, in order to scale dichotomy of control to larger scale multitask settings, there are more challenges associated with it, which we detail more in the foundation model for decision-making review paper that you're welcome to check out. And please, thank you, please check out our paper and poster, which is today at 11:30 a.m. at booth 119. Thank you.